Good day again, grade 11s and 10s, and welcome back to another video on REDOX reactions. This is actually the last part of REDOX reactions. I hope you are all excited for this one. So today we're going to be looking at how to actually balance redox reactions. You know, we're dealing with chemistry. Everything in chemistry just needs to balance. That's why we say chemistry just balances your life. But anyway, that was meant to be a joke, by the way. But anyway, we're going to be looking at balancing redox reactions, and we're just going to focus around the necessary gymnastics to familiarize yourself with to actually master the balancing of redox reactions. Not really hard in any way. It's actually not hard at all. So if you can just follow and we can just work cohesively and try to attempt a few of the examples that I give, and then you just to test your understanding, and from there I promise you everything is just going to be smooth sailing, especially in an exam, because we are all doing this to get that distinction. But so today we are going to be looking at balancing redox reactions, as I've said. And what I usually do is I always like to have a certain steps, you know, that would call tips rather, that are very important and to consider when you do certain things. I only give you steps if I know that you need them. They actually matter. So in this particular case, I'm going to give you a few steps on how to basically balance redox reactions, right? So it's just going to give you a few steps. So step number one, must make sure that, so given a certain compound, you must identify, right? So you must identify, make sure that you identify the oxidation numbers. Make sure to identify the oxidation number of each given atom or element in this particular case. And how do you actually do that? You use your rules, right? But how do you actually determine the oxidation number? You use the rules and your basic knowledge. That is, if you have some oxygen alone, you know that it has a charge of oxidation number of 0. And if you have oxygen in some other compound, then you know it has an oxidation number of 2 minus, given that it's not a peroxide or a fluorine. Right. So identifying the oxidation number of each atom or element basically helps you identify what oxidizes and what reduces. Identify what oxidizes and what reduces. What oxidizes and what reduces. Basically helps you identify what oxidizes and what reduces. So that's number one. Right, so this is a very fundamental point. I'm just going to add some black. I should make them in black, because the blacker it is, the more important it is. Not black, but red. Let's make this very important. Very, very important. Cool. Now the second step would be, now once you've identified what reduces and what oxidizes, you can then write out your oxidation reduction reactions. So write down your oxidation reduction half reactions. Half reactions. Oxidation reduction half reactions. That's what you need to do. Write down your oxidation reduction half reactions. I'm going to get to what that is exactly, but just keep this in mind. So you need to write down, and with that, make sure that you balance your electrons. That is very important. Balance your electrons. Very important. Again, in red. Very, very important. Balance your electrons. Fundamental point. Right. And then back to my black. Right, and then with the third one, all you have to do is just write your net reaction. Write net reaction without electrons. So make sure that once you've balanced your electrons, you need to make sure that they cancel out without electrons. So Right, so if you look at a certain example, so say we're given, not given rather, but assume we have some element y and some other element z. These are not real elements, these are just some letters that I'm using right now. And say that element y undergoes oxidation. So element y oxidizes and element z reduces. So what do you then do from here? So once element y is identified to be the oxidizing one and z is identified to be the one that reduces, we all know, well, you should know now that since it oxidizes, it's the reducing agent, and since it reduces, it's the oxidizing agent. But in this particular case, how do I write down what I call my oxidation half reaction? So the oxidation half reaction is, as the name is given, it's the reaction of just the oxidizing part. That is, whatever it is that oxidizes gets this particular reaction. So since we say Y oxidizes, so say Y is a some element in group 2, right? So say it's some element and it's in group 2. What does it tell you? It has a charge of positive 2. Just an example. I'm not saying it always has. Y is not even an element. Just an example. Right, so I would then have y2 plus, right? And then y2 plus will obviously, what do you know about a substance that has a positive charge? In fact, what does the charge of a substance or of a certain element tell you? So if I have some element, um, magnesium, which is magnesium 2 plus, this 2 plus basically tells you the number of electrons lost. So in this particular case, what does that mean? That means this lost 2 electrons. That's how it always works. Even if it was a 3 plus, tells you that it has lost 3 electrons. If it was 20,000 plus, tells you that it has lost 20,000 electrons. By the way, there's no charge. There's no such thing as a 20,000 charge. But yeah, I just really hope you got the idea. Okay. So, I mean, similarly to the fact that if something has a charge of, say, oxygen 2 minus, that basically tells you that oxygen, so when the charge is negative, it's a gain of electrons. It's a gain of electrons. Therefore, oxygen gained how many electrons? Aha, gained 2 electrons because it has a charge of 2 minus. Even if you have a charge of 7 minus, you gain 7 electrons. 1 million minus, you have gained 1 million electrons. Right, so the positive charge means you lost electrons, and the negative charge means you gained electrons. So Y2 plus basically means that it lost 2 electrons. So these are the 2 electrons that it lost. And then it forms a clean, pure element Y. Right, so this is what happens. But because this is an oxidation half reaction, when something oxidizes, what does it do? It loses electrons. So it moves from being 0 to being a positive 2. So it must be an increase in oxidation number and a decrease and the loss of electrons. So I need to flip this equation, swap. So I need to have something like Y gives me Y2 plus 2 electrons. Why? Because now we had an oxidation number of 0 here. We have an oxidation number of 2. It must move from 0 to 2 to say that it oxidized, right? Oxidation number increases. It also lost the 2 plus here. Tells me that it lost how many electrons? 2 electrons. All right, I really hope you guys are seeing that. Okay. So it's lost 2 electrons. Just going to remove this. Right, so a typical element Y, right, undergoes oxidation and thus makes this equation. So it's Y gives me Y2 plus the number of electrons lost. And then if they asked you for the reduction half reaction, reduction, half reaction, reaction. Okay, pardon the spelling there. Right, so the reduction half reaction would then be Z, right, 2 plus the number of electrons gained gives me a pure element zinc. Sorry, not zinc, but just Z. Now notice something. In these two, I moved from something with a charge of, with an oxidation number of 0 to an oxidation number of 2. The oxidation number increased, therefore it undergoes oxidation, right? But also notice something. Remember, when something oxidizes, it loses electrons. So it gives away electrons, right? So when you lose electrons, whatever it is that you've released becomes your product. That is why your electrons are in the product part. That is why they're used. I mean, the electrons become the products because it's what you have released. But when you gain something, you gain it and that becomes a reactant. That is why Z has 2E minus in the reactant side, because you gained those electrons. Okay. Now, if I had to use these two, the oxidation half reaction, and by the way, when they ask you for the oxidation half reaction, please just write down the half reaction for the one that oxidizes, and that's it. Please, they're going to be specific. Oxidation half reaction, reduction half reaction. Or they can say, write down the net reaction. So they may ask you, in fact, they will ask you for the net reaction. So what exactly is that? The net reaction is the reaction that you have as a product, I mean, at the end, when you've removed your electrons. So in this particular case, with these two examples that I've made here, this is how I would have my typical net reaction. So you start here with these two half reactions. I'm just going to remove this. Hope you have that down. I'm just going to try to bring this a bit up. Just bring it up a bit. Right there. Okay. So what did they notice? Well, for starters, your electrons. Now, before we write down, we need to start going back to our notes. The steps. So what are the steps? The steps are identify the oxidation numbers of each element. We've done that, which helps you identify what oxidizes and what reduces. So like I said, we identified Y as the one that oxidizes and Z as the one that reduces. Then step 2 says, write out your oxidation half reactions. We've done that. And balance your electrons. That is, if I have 2 electrons on the reaction side, I must have 2 electrons on the product side. So notice something. I have 2 electrons on the reactant and 2 electrons on the product. Are they balanced? Yes. That is the only time you are able to cancel out your electrons, if and only if they are balanced. Meaning if I have 2 on the reactant, I must have 2 on the product. 1 on the reactant, 1 on the product. 1,000 on the reactant, 1,000 on the product. 5 on the reactant, 5 on the product. That's all that they mean. Now, if I write down my net reaction, it will then be everything that's on the right, everything that's a reactant will be added to everything that's a reactant, and everything that's a product is added to everything that's a product. That is, if I have my Y here as my reactant, I write it down. What else is my react? So I have equation 1 and equation 2. So in equation Y is my reactant. Equation 2, Zn2 plus is my reactant. I then say in equation 1, what is my product? Y2 plus. And equation 2, what is my product? Zinc. And that is then my net cell. Sorry, my net reaction. Okay. Without, like step 3 says, write out your net reaction without the electrons. Okay. Alright, really hope that was clear. But anyway, just to make it a bit more clear, we're going to do like a couple of examples. Alright, so just going to do a couple of examples just to clarify everything. So I'm going to have example. So example 1. So example 1 would be that reaction that we had earlier, which is magnesium in the first video plus oxygen. That would give us 2 magnesium oxide with 2 magnesiums right there. Right, so that's a reaction that we are given. So what exactly do we do now? So now we go to step one. What does step one say? Identify the oxidation number of each atom. Okay, so let's do that. What's the oxidation number of magnesium? I hope you scream to the top of your voice and actually say it as 0 because it's a pure element. What about oxygen? Yes, 0. What about magnesium in MgO? Aha, 2 plus. And oxygen? Definitely 2 minus. Right. Now notice something. The oxidation number of of magnesium increased. So it moved from a 0 all the way to a positive 2. And what about that of the oxygen? So the oxygen oxidation number decreased. Why? Because it went from 0, oopsie, oopsie daisy. So it went from 0 and all the way to a negative 2. Oh my gosh. Remember, negative 2 is less than 0. So when you get from 0 to negative 2, you decreased. So how do you know about something that decreases on oxidation numbers? What does it do? Aha, it reduces. Decrease in oxidation number, reduce. Increase in oxidation number? Yes, oxidize. So we say that magnesium oxidized and oxygen reduced. Now remember what we call these. We say this guy here is our reducing agent. And this guy here is our oxidizing agent. Alright, so now we must write down the redox, oh, Jesus Christ. So sorry, not the redox, but the reduction and oxidation half reaction. So we're going to start with the oxidation half reaction. So this one is for magnesium, the one that oxidizes. Now notice the form that it takes. It's always the pure form first, then the element with the charge, and then the number of electrons that it's lost. Since magnesium is a 2 plus, we then say that's magnesium to give me Mg 2 plus. How many electrons did it lose? Because of the 2 plus, that means it lost 2 electrons. Right, and then what about oxygen? So oxygen wants the reduction half reaction. So notice something. With the reduction half reaction, we have first the element with its charge. So we have the ion and we have the number of electrons lost and the pure form is a product. So in this particular case, we're going to have oxygen, right? We would have the oxygen O2 plus 4 protons plus 4 electrons, and that would give me, let's make this 2 arrows for the sake of it. Right, and so that would give me 2 water molecules. Right, so what do we then notice? We then notice that we have now our reduction. Oh, by the way, in case you're wondering where I get all these, I get these from what we call the table of standard reduction potential. So when you do a chemistry paper, you would have that very long table 4A or table 4B, and then you would get these typical reactions from that particular table. Right. So now what do we notice? What does step 2 say? So did we write down a reduction of reactions? Yes, and now we need to balance our electrons. Are they balanced? No. Why? Because on this side, I have 4 and I have 2 here. So what do I have to do? Multiply everything in the oxidation of reaction by 2, so I can get these 2 electrons to be 4 electrons. That is, if I have something like this, I do that. So I just multiply everything by 2. So what I end up having is this. So I'm going to end up having 2 magnesium to give me 2 Mg2 plus 4 electrons. And that will then be O2 plus 4H plus 4 electrons to give me 2H2O. Right, we're getting this, we're getting something. Right, so are we done? No, not yet. Are the electrons balanced? Yes. Now what does step 3 say? Step 3 says write down your net reaction, your net ionic reaction. Then that will be, are the electrons balanced? Yes. Can we cancel? Definitely. So there goes 1, 2. And for the net ionic reaction will then be 2Mg plus O2 plus 4H plus. That will give me 2Mg 2 plus 2 water. And that is then our final answer. Now notice something. Whatever was my reactant was put together with everything that was my reactant. And anything that was my product was put together with what was my product to form this and that. Similarly, to form this and this with that as well. So I hope you guys are seeing this. Really hope you guys are seeing this. Alright, so let's just do more example, just another one. So this one would then be we are given magnesium that reacted iron sulfate, and that forms magnesium sulfate plus iron itself. Now step 1 says identify the oxidation numbers. So what's the oxidation number of magnesium in this case? Yes, you're right, 0. And then fluorine, aha, 0. Why? Because they are pure elements. Yes. Right, so what's the oxidation number of fluorine in FeSO4? Now remember, FeSO4 is SO4 2 minus. That means it must be with a fluorine that's 2 plus, so these can cancel and form that. Therefore, the oxidation number in this case of fluorine is a 2 plus. So the oxidation number of fluorine is 2 plus. Just that. So fluorine is positive 2. And magnesium is also positive 2. By the way, we don't need to really worry about this because it's like a spectator ion. So it's just the same in both the reactant and the product. So if you had to determine the oxidation number of sulfur, it would not change in both the reactant and the product, as well as oxygen. So that's why we really don't consider those. But if you notice something, if you look at the oxidation number of of magnesium, and we look at it here, notice something. Oopsie daisy. Ooh, got a bit back on that one. Okay, so notice what happened. The oxidation number of magnesium increased from a 0 to a positive 2. What do you know about this? What do you know about a substance that has an increase in oxidation numbers? We say that it oxidizes. And then if you take a look at iron, the iron number decreased from a positive 2 to a 0. Ooh, what does it tell you? Decreased from a positive 2 all the way to a 0. What does it tell you? It reduced because it decreased in oxidation numbers. Now we've identified our magnesium and we say that it oxidized, and our iron was reduced. Now the oxidation half reaction would then be just use a different color, says pink, so that would be Mg to give me Mg 2 plus 2 electrons. And then for the iron, because it's Fe2 plus, it would then be Fe2 plus 2 electrons to then give me pure Fe. Right. Okay. Really hope you are fine on that one. Everything is well. We are not confused. Again, if you are confused, please talk to me and I will definitely help you out. Okay, now we can write our net reaction. Ooh, not too fast there, Munchie. We need to first balance our electrons. Are they balanced? Yes. Can I cancel out? Yes. 2 electrons cancels out 2 electrons. Can I write down my net ionic reaction? Yes. Yay! So I will then say magnesium reactant with reactant plus Fe2 plus gives me product with product. Mg2 plus Fe. Really hope you guys are getting this. We are done with this. And just the last example, just to actually embed everything into that smart head of yours. So we get the last example. And this is example number 3. So say we are given copper oxide. So that's CuO. And we react that with H2O. And that will give us, pure copper and water. As the British would say, water. Okay, so now we have this. And what do you notice? Since this is copper and just copper, what's the oxidation number? Yes, 0. And then hydrogen? Aha, 0. Right. And then in copper oxide, so sorry for the noise. Just get a little bit too excited. Okay, so copper oxide, right? So what's the oxidation number of copper here? It's actually a 2 plus, and then oxygen is 2 minus. But let's see, let's test it. Since this is a pure compound, we know that's 0, and you know that's copper plus the one that's oxygen, which is negative 2, and that's 0. So that's Cu minus 2, that's 0, and that gives me Cu equals to a positive 2, right? So that's how I actually got to that conclusion. Okay, right, so what then? From here, what's the oxidation number of hydrogen in water? So we know that's H2O, which is equal to 0 since it's a neutral compound, and that's 2H plus the one of oxygen, which is negative 2, which is 0. So that's 2H, which is equal to 2. Therefore, H is positive 1. So that's a positive 1. And then the oxygen here is negative 2. Right. Okay, just to erase this. Now let's see which one oxidizes, which one reduces. We don't know. Let's find out. So notice how copper moved from a positive 2 all the way to a 0. Oh my gosh. And hydrogen moved from a 0 all the way to a positive 1. By the way, I don't actually focus on the oxygen because notice how it's the same. It neither reduced nor oxidized. So in this particular case, notice how Cu2 plus becomes Cu0. Did it increase or decrease? Decrease. Is it oxidizing or reducing? Yes, reducing. And then what about hydrogen? Increase or decrease? So it went all the way to positive 1 from 0. That means it increased, thus oxidize. Okay. And then from here, what do I then say? So I know that copper reduced and oxygen oxidized. Right, so if I have to write down my oxidation half reaction, I'll then have that's Cu2 plus 2 electrons to give me pure copper. By the way, like I said, you get these reactions from the table of standard reduction potentials. You will be given this table in an exam. Right, and then for oxygen, oh, I literally just said oxygen. I'm so sorry. So sorry. It's supposed to be hydrogen. Hydrogen will then be, so for hydrogen, we have, so that's, if I remember correctly, that's H2. Okay, yeah, plus 2 protons to give me, wait, is it 2 protons? No, sorry, my bad. It's supposed to be H2, which will then give me 2 protons plus 2 electrons. Yes, that's how it should be. My bad. Right. Like I said, get all of these from your table of standard reduction potentials, just in case you're wondering, where does it get all these numbers, all these reactions from? Okay, so here's a question for you. Is this equation balanced? Yes, no, maybe? Are the electrons balanced? Yes. Cancel out. Can I write down the net ionic reaction? Yes, then let's do that. So this will then be copper 2 plus, that's reactant with reactant plus H2 to give us product, which is copper, plus product, which is 2H plus. And that is our final answer. So that then gives us the final answer. Right. Really hope this was fun for some of you. And yeah, we're gonna end the video here, and that brings us to the end of redox reactions. And in the next video, we're just gonna be doing a couple of past papers, you know. But from me to you, I shall see you next time. Thank you for watching. Bye bye.